All right, let's move it into chapter 40. Again, we're not going to do a tremendous amount here with chapter 40, but we will try to explain electron orbitals and talk about a little bit about quantum mechanics and quantum numbers. So this is actually called All About Atoms, this chapter. We're going to talk specifically about electrons in this chapter, but quantum mechanics, quantum numbers are things that would govern a lot of small things. So quantum mechanics is the idea of governing things which are extremely small, the laws of physics that deal with things which are small, at the very small sort of nuclear atomic level. So each electron has 4 quantum numbers, any bound electron. It has little n, the principal quantum number, and this is the n that was in our our n sub n in our E sub n equation. So minus 13.6 electron volts over n squared. This is that n. It'll tell you what orbital is it in, right? Where is it? Is it the n equals 1 state, n equals 2 state, n equals 3 state? So that's our principal quantum number, little n. There's also an orbital quantum number, little l. So orbital quantum number, and I'm not going to talk about what this actually physically is describing. It has something to do with angular momentum of our electron inside the orbital, the principal quantum state that it's in. So L can range anywhere from 0 to n minus 1. They're integers, so L has to be an integer, and for any particular electron, it will have an n, that's its principal state, and the L that it has to be 0. It can be 0, but it has to be less than n. So it has to be n minus 1. It can highest it can go. We'll do a little bit. I'll do some examples here in a second. Then there's m sub L, which is the magnetic quantum number. It can range from negative L, jumping by integers, up to plus L. Again, this has to be an integer. It can go anywhere from negative L up to plus L. So depending upon what L is for this electron, there's limits on what m sub L could be. And then finally, the last one is m sub S, which is the spin quantum number. And m sub S just has 2 choices. It always has 2 choices. It's either negative 1/2 or plus 1/2. Only negative 1/2 and plus 1/2. That's specific to a type of particle like an electron that has 1/2 spin. So it can have either down by 1/2 or up by 1/2. There's a lot more that goes along with this that you would learn in quantum mechanics. So let's say an example, let's say we have an electron that has n equals 3. That's its principal quantum number. This electron could have an L which is 0. It can have an L which is 1, or it can have an L equals 2, right? L has to go anywhere from 0, but it has to stay less than 3. But 2 is less than 3, and so it can be 0, it could be 1, it could be 2. Let's say L was 2 for this specific electron. Then that electron could also have, it could have m sub L equals negative 2, negative 1, 0, plus 1, or plus 2. So it has all these different options of what it could have as its magnetic quantum number. And then no matter what, its m sub S can either be negative 1/2 or plus 1/2. Let's do another example. If you have an electron which has n is equal to 1, well then if n equals to 1 and L has to be 0 or stay less than 1 than n, then L can only be 0. For an electron that's in the n equals 1 orbital, L has to be 0, and then that means m sub L has to be 0. And m sub S, the only choices are either negative 1/2 or plus 1/2. The Pauli exclusion principle says, and this is also part of chapter 40, is that in any particular atom, no electrons may have the exact same set of 4 quantum numbers. So there's no electrons can have the same ones. You can't be in the same one. I saw a really great meme that only physicists enjoyed, which said that objects like an electron, which is a fermion, which follow the rules, the Pauli exclusion principle, they do social distancing because they can't share the same quantum numbers. whereas things like bosons can share the same quantum numbers. But an electron is a fermion, and it can't have the same amount. So if you say we're building, and this is not just true for hydrogen, this is true for any atom. So in the n equals 1 state, so I made a little table here. So if n equals 1, L has to be 0, m sub L has to equal 0, but you could have negative 1/2 and plus 1/2, right? This would be two different electrons. This would be electron number 1 and electron number 2. And they don't share the same, all four. There's something different. They have that fourth number is different. And so there's two allowed electrons in the n equals 1 state. In the n equals 2 state, now we've got n equals 2. Oops. N equals 2. And I said, okay, L equals 0, M L sub equals 0, right? If L is equal to 0, M sub L equals 0. So we have negative 1/2 and plus 1/2. Again, that's 2. But then if n equals 2, L could also equal 1, which would allow M sub L go from negative 1 and 0 and plus 1. And for each of those M sub L's, there's a negative 1/2 and a plus 1/2, a negative 1/2 and a plus 1/2, a negative 1/2 and a plus 1/2. And then all of 8 of these electrons have a different set of 4 quantum numbers. So there are 8 allowed electrons in the n equals 2 state. I could go through, and for n equals 3, what I would find is that there are 18 allowed electrons in the n equals 3 state. This allowed is because they will have different sets of those 4 quantum numbers. That's what determines this. That's what determines this. The number of allowed electrons in an n equals state of any atom is 2 times n squared. You've probably been taught this somewhere along the way. I know I was taught that. You can put 2 electrons in the first shell. You can put 8 electrons in the second shell. You can put 18 electrons in the third shell. This is why. The Pauli exclusion principle is why there are these limits. And the quantum numbers that we're talking about are n little l, m sub l, and m sub s. Number 4 asks you to go through and figure out the number of allowed electrons in each shell. We call the L, the little l, the subshell. The number of electrons allowed in each subshell is 2 times the whole thing, the whole addition of 2L plus 1. And number 6 wants you to go through and look at that. These are questions from chapter 40. So how many electron states are there in these subshells? And 4, L3, and 3, L2. The subshell is what determines how many can be in there. Now, the subshells and shells have got letter names that I don't know how much physicists use these subshell and shell letter names, but I know that they are prolific, especially when people are talking about this in chemistry. So the shell, again, is N. So I usually refer to shells by the N number, but they can be referred to by these capital letters, capital K for N equals 1, capital L for 2, and capital N and M and N. And again, the number of electrons in the whole shell are here, 2n squared. But the subshells, again, this doesn't matter what n you're in, except for the fact that you're not allowed to have an L equals 3 unless n was equal to 4. But subshells, when you have L equals 0, is little s, little p for 1, little d for 2, little f for 3, and little g for 4. And the number of allowed electrons in the subshells, again, comes from this 2L plus 1. And we can see that even here, right? For even our n equals 2 situation, when n equals 2 but L equals 0, I still only had 2 electrons in that subshell. This would be 2s. And then here's the 6 that were in the p when L equals 1. So that would be 2p6 is how they write it. Let's look at some more with this really quickly. filling up these. So determining your electron configuration. The subshells with the lowest N plus L are filled first, with the lowest N is preference. So you do the lowest N first before you do that. So number 31, let's look at that. Actually, what did I do with the book? There's the book. Number 31. And chemistry students, I'm sure, are like, I got this. But for those of us who are not chemistry students, let's think about it. So number 31 says, we're just going to do selenium, which is the first one. It says selenium, where it says capital Z equals 34. So capital Z, that's the number of protons officially for selenium. The number of proteins tells you the number of what the atom is, what the element is. But if it has 34 protons, let's assume it also has 34 electrons. And then it wants us to take this writing right here, 1s, 2s, which I've rewritten down here in big on my notes. And it wants us to write in how many electrons are there. And so what you do is you actually put a little superscript next to the letter. So 1s, what that means is, actually I'll rewrite it. So what that means is, oh goodness, that's not what I meant to do. So I'll write what the N is and what the L is for each of these. So N is just the 1, and the S, right, the S is L equals 0. So that. Here the N is 2, the L is 0. Here the N is 2 and the L is 1. Here the N is 3 and the L is 0 because it's S. Here it's 3 and 1 because the P means 1. Here it's 3 and 2. D, little d, is 2. Here we have N equals 4. S still means 0. And then here's 4 and 1. And so when we have N plus L, this is 1, 2, 3, 3, 4, 5, 4, 5. And so this is our N plus L's. This is going to tell us the order that we have to fill up electrons in. And then we say, okay, well, the 1s, this is the one that I can put 2 in. And so we say 2 electrons there. And I'm going to put a running total of how many electrons I've got in there because I'm trying to get 34. So I have 2 after I put those in there. Here, this is an S. I can only put 2 here as well, right? In the S subshell, I can only put 2 electrons. And so now I have 4 total electrons. The P, I can put 6 here, and I'm going still in order. So this was N plus L is 1, N plus L is 2. Here I've got N plus L is 3, and this is 3 too, but this has the lower N. So I'm going to fill that one up first. I'm going to put 6 electrons in there. 6 plus the 4 I already have gives me 10. Now I go to the next 3, and I can put 2 in this because that's an S, so I end up with 12 total. Now I need to go to a 4. I've got this 4 and that 4. This has got the lower N, so I'm going to do this one first. That's a P shell, subshell, so I can put 6. So now I have 18. That's 6 plus the 12. But now I'm going to skip. Before I put things in 3D, I'm going to go to 4S because N plus L is 4. And S can have 2 in it. Right? So 2 plus the 18 gives me 20. So I'm going to skip and do this one first. And then I'll come back to 3D. Now D can have 10 electrons in it. And I still have 10 more electrons. I have 14 more electrons. So I can put 10 electrons here, which will bring me to 30 total electrons. And now I can move over to this last one. I've got 4 more electrons to put in here. Right, I only have 34 total. bringing me to 34. And so this is how we write the electron configurations. And they look ridiculous in my opinion, but that's how it's done. You sit there and you write them out like that. This is a Wolfram Alpha demonstration also of this, where they're really showing us the N plus L. So there it goes. So here's just our options. So 1s, 2s, 2p, 3s, 3p, 3d, right? This is another way of writing this thing that I've got written out. We'll go ahead and check. Let's go ahead and put, we want selenium, which is 34. Whoops, come back. Can I step this down? There we go, 31, 33, 34. And they're really only showing us the last bits here. They're showing us 4s2, right? 3d10 and 4p4. And that is what we had. And again, you could ask it to show us the N plus L's as well. And you would go in order here of this arrow, right? So we're going to fill up 3D before we do, and then we do 4P, and we didn't end up needing 5S. Right? These are the ones that have N plus L equals 5. Y'all are supposed to do the other ones number 31. So you're going to do bromine, which is Z35, and krypton, which is Z36. But this is why the shells fill up the way they do for the electron configurations, and why we end up with limited amounts of electrons in various subshells is, again, the Pauli exclusion principle. And that's all I have for chapter 40. We're not going to do anything else in this chapter, which is disappointing because there's a lot of different things here, including lasers, but we're going to move on. The next chapter we're going to cover will be chapter 42, and then we'll do chapter 43. We are not doing chapters 41 or 44. All right, y'all. Bye.